Hello everyone and welcome back to this next lecture. So this is where we had left off in the last lecture, where we had run the simulation and we had verified that no errors were showing up in the console. And since no errors are showing up in the console, we can go back to the circuit simulator and we can start creating some plot files. So now plotting any of the circuit meters, that is either the ammeter or the voltmeter, will be completely useless. The reason is we are not generating any gating signals and therefore the whole circuit is going to be dead, right? Except maybe the input voltage, which will show the constant input voltage, but that pretty much is useless. So first what we're going to do, since the simulation is still running, we can just add a plot and we can plot our carrier waveform to at least verify whether we are getting the correct carrier waveform. So I'm just going to call this carrier. The title is totally up to you, and we are going to choose the last one. See, all the meters, any meter that you create will automatically show up in the waveform source. So these are all sources that you can add to any plot. You can also add any variable storage element as long as you have set the storage status to yes. And for the PWM carrier waveform, we had done so. We had set the storage status of that variable storage element to yes. So we can add this. Now the waveform legend is merely that if you have several waveforms in a single plot, it will create a legend and it will show you which curve belongs to which variable. So I'm just going to call this C, something that to identify with. Save the waveform. And I will click on done because we are not looking for anything else. So with this we have this one plot. Now the normal way of plotting this is to click on this plot button and it will generate a PNG file, right? But however, in the latest version of Python Power Electronics, I have created another way of generating plots, and that is using matplotlib. And I would strongly recommend that you use this method because it is much more robust than generating PNG files, right? So I will let this process complete. So the page is refreshed, which means that the plot has been generated. So if we go over to our file browser, you will see that there is now this carrier PNG. So you can open it and view it, but it's pretty much useless because it plots the entire plot, right? And this is why I say it's better to use matplotlib, because then you can zoom in. So I'll show you how to use matplotlib. So the first thing we're going to do, we're going to go over to our circuit simulator and we're going to click on this export to matplotlib button. What this will do is it will take each and every plot that has been defined. So you can define n number of plots, and I will show you how to do that later because I'll be doing that very soon. You can click on that and it will take each and every plot and it will create a new plot figure in exactly the same way as we did before. Only it will take care of all the other details, such as extracting the data from the simulation output data file. So I'm going to click on this export to matplotlib, and let us go over to our code editor and let us check out the files generated. Now the default file name when you export this, when you click on the export to matplotlib button, is this file autoplot.py. Alright, this is what the circuit simulator generates automatically for you. So you can look and see what all it has. It uses the same, that is, it uses NumPy, it uses matplotlib, everything else. It reads the circuit output.dat file. Alright, it reads it and uses something called pandas. Now I don't want to go into the details of pandas yet. It is used for dealing with large data and is very popular in data science, right? Now this one is going to take this file, that is, it's going to now extract whatever file you want and it is going to put it into this particular figure. So for example, all these are merely some styling. You don't have to worry. It just sets the font of the any letters within the plot will have a 12-point font, and it just sets the family to be normal so that it uses the base base font which is there in your system. That's all. Here of course you see this is the plot.figure file. It gives a title equal to the name of your plot, right? So we have named it carrier, and therefore the plot title is carrier, and it gives an X label which is time because the plots are with respect to time. And here it extracts the corresponding column. You don't have to worry about this. It extracts the corresponding column and it uses and it gives a label which you have provided, right? So for example, sorry, I used the wrong one. We have provided the label C, and therefore the waveform has a label C, but this is something you can always change, right? It also saves it to an EPS file. I'm going to comment this out because we are not looking at EPS files. This however is very useful if you want to generate publication quality plots, right? So let us go over to a command line. Now I would not suggest that you switch off your circuit simulator. I'm going to open another terminal. Alright, so in the next tab is open in my terminal. So you can have, most terminals allow you to open multiple tabs. If you're using Windows, you can just open another Anaconda prompt or another Anaconda PowerShell, whichever you prefer to use, right? So the first thing we need to do, we need to change directory to the document folder. So I'm just going to do CD and then go to documents and then go to the switching strategies directory, go to modulation and go to buck converter. So this is where our autoplot.py is. So I'm just going to clear the screen. So we are in the right folder. The next thing which we need to know is that we are in the base environment. So we can't stay in the base environment. We have to activate our circuit sim environment. If you want and you do not want to mess up your circuit sim environment, you can also activate the SP environment. That is also okay, because remember, we are only generating plots. We are not doing anything with the circuit simulator. The circuit simulator is just created a matplotlib file with which we can run or at least generate plots. So here we will have to do one small change, and I will show you what that is. So I'm going to go and run this autoplot.py file. There will be an error, but I would like to show you the error and tell you how to resolve the error. So you see, it will say no module named pandas, right? This is because pandas has not been imported yet, which only means we have to install it. So let's go and install it. So as usual, I'll clear and then say conda install pandas. So as before, the installation of any major package usually has dependencies, and also this pandas also has certain dependencies. So this merely says, can it do so? The answer is of course yes. And as usual, this will be a long download. So I will pause the video and come back when it is done. So the installation is finally complete. So with this, let me clear my screen. And let us now run that command again, that is Python autoplot. Now it should work because the NumPy and matplotlib are already there, only pandas was missing. So let's see what happens. So here is the plot. Okay, now here there is some kind of messages, which means the font family normal has not been found. I would say if you really want this to be resolved, you can Google it. But this really is question of what is installed on your system, right? So you can play around with some, like you can put in Arial, or you can put in Helvetica, or you can put in Times and check out if any of those show up. Otherwise, it doesn't really matter. It will use some default font, so it doesn't really matter. So let me expand this, and what we are trying to do is verify whether we indeed have a sawtooth waveform. So now let us zoom in. And let us try to get, let's say, 2 to 3 cycles. And this is it. All right. So the good news is we do have something that resembles a sawtooth. So like, for example, it starts at 0, it goes up to 1, drops drastically back to 0. So this is a sawtooth as opposed to the carrier waveform. The reason is it resembles the tooth of a saw, right? That's why it's called a sawtooth. Now, this sawtooth waveform, if you have a look, let's look at the time period, because we've verified that the magnitude is okay. We've also verified that the shape is okay. Now let us look at the time period. So if you see, this is the 0, this point, that is 0.0002, that is 3 zeros and 2. And the next 0 is at 0.0004, that is 3 zeros and 4. So the difference between them is 0.00002, that is point and 3 zeros and 2, and therefore, as we already know, if we take the reciprocal of this number, it's going to be 5000. So our carrier waveform has been correctly generated. This is what it shows. So the advantage of using this method of plotting is that we can very conveniently generate plots which we can zoom into and which we can play around with, and which already comes with all the other features, such as it comes with the title, it comes with the label, and it also comes with the legend, right? So I'm going to close this down. Now that we have verified our carrier signal, let's go back to the circuit simulator, and we can actually stop this, right? Because we now have done the first part. So let me go back to my code and the PWM code, and here. So we have now verified our carrier waveform. Now we are ready to implement our modulation scheme, PWM. So let's go back here, or rather here, and we can implement this thing. So usually this logic will work in almost all cases unless you have a special case for which it needs to be inverted, right? Usually if the modulation signal is greater than the carrier signal, we can turn on a switch. If for some reason you need to invert your logic, then you need to think why you need to do so, and in that case you need to invert the logic. That is, in that case switch will be -1. But for most cases this logic is good enough. So let's just code this logic. So let's come over here. We have defined a duty ratio. So let's come over here and do that comparison. Actually we should just write it. So this is, we should call this modulation carrier comparison. As I already said, I just like to write a lot of comments because that's the only way I can keep track of my programs. Would strongly suggest that you do the same, though it is not compulsory. They are not executed. It's just for you to remember what you've done, right? So if the duty ratio is greater than, now here it's up to you whether you want to say greater than or equal to or greater than. So if you go back here, we have done the reverse. This is totally up to you, right? You can put the greater than or equal to here, or you can make it less than or equal to here. That's not a problem, right? So I can just leave it the way we've done. So I'll just say if it is greater than the carrier waveform, then in that case, what do? Now we need to give a gate signal. So let us say we define a gate signal, that is S1 gate, and this is going to the device S1. That is, let's go to our Excel sheet. This is this device here. So we are now going to use our modulation scheme to generate gating signals for this device. Now again, if you are familiar with Python Power Electronics, you will know that if I give a gate signal of 1.0, it will turn on the device, right? And if I give it a gate signal of 0.0, it will turn off the device. That's how it is, right? So I can just say that if it is not this case, that is if it is less than, or the duty ratio is less than or equal to the carrier waveform, that is the else case, that is the else condition, I will just say S1 gate is equal to 0.0. Alright, so this is a turn on, this is a turn off. Now how are we going to connect this logic to our actual circuit? And for that we need to define an output variable. So let's go back to our circuit simulator. Let's go back to the control, and here we need to configure the control. We need to add another control variable that links whatever code we've written to the circuit. So any control variable, when you define a control output, this will have a list, that is, it takes the output target and it gives you a drop down list of all the output, all the controllable variables in your circuit. In our case, we have only one controllable variable, which is the switch. The diode, even though it is non-linear, is not controllable. So therefore there is no, it doesn't show up here. So we don't have to do anything. The only thing is the desired variable name and control code. We have already given it a variable name. So let's go and copy it. And let's come back here and let's paste it. So the initial value of the output can be something, just so that in the beginning when it starts, the circuit simulator needs to initialize all variables. It needs to give a sensible value, right? That's all it matters. So with this, I'm sorry, I pressed Control Save. I don't know why. So I will save this output and make sure that it shows up here. So we now have linked our control code to the circuit, right? This is all done internally by the circuit simulator. You don't have to worry. You could say it is the equivalent of defining an output variable and connecting it to a device in MATLAB or PSIM, right? Something similar to that. So with this, let us go back. We are now ready to run our circuit, because now we've done everything, right? We have generated a carrier signal, we have chosen a duty ratio, we have performed pulse width modulation. So let's go run it, right? Now it says the simulation is running, but like I said, always go to the command line and check if there is no error. And you see we don't see an error. So that means the simulation is indeed running. So now that we have this, what we can do, we can start generating some more plots, right? So we can add a plot. So we're back in the simulator after verifying that our simulation is indeed running. So now we already have this carrier waveform plot. And since the simulation is running and we have also completed our closed loop control, let us go and add some more plots. Okay, let us plot the currents and let us plot the voltages. So let's create a new plot. And in this, let us plot the currents, right? So let us say this is currents. And here we can plot some of the major currents that we know. For example, we definitely want the inductor current, right? That is a major variable that we want to see. So let us name this IL, right? Now we will be plotting multiple waveforms in the same plot. So it's important that we do name them. So here you see they will appear in the list, right? Ammeter L1 is called IL. The next one, now we can plot ammeter CO, which is the current through the capacitor, but this is a little difficult to interpret with respect to operation because it's more of a ripple current. So instead, let me plot the input current, that is I ammeter Vin. So I will call this In. Save the waveform, and you can see they all start appearing in this list. And of course, the last one is, let's say, the load current, right? So we will call this IO. So I will save this again. Make sure they all appear here. If you want to plot any more waveforms, please do so, right? There is, after all, the ammeter, the capacitor current. There is also, I can't think of anything else, but if you want to plot any more, by all means go ahead. But I think I'm done with this. I'm going to click on done. And now that we have the currents, let's go and plot the voltages. So I will create a new plot and I will call this voltages. And I will start the plot. And let's come over here. Not here. So I will plot, there are two major voltages which are important, which we have. That is voltage input Vin. Though it is a constant, it still is the input voltage, so it should have it. Make sure it appears in the list. Then after that there is the output voltage, and I will call this VO, right? Now if you have measured any other, for example, if you measured the voltage across the inductor or anything else, by all means you can plot those as well, but I will click on done. Now as before, if you really want, you can plot these by clicking these buttons. You will get a PNG file, but remember, it's not very easy to deal with those PNG files, and you will have to use the start stop in order to zoom. So what I would recommend is click on this export to matplotlib button as before, and then let's go over to our code editor. So in our code editor, if you look at the browser and we open autoplot.py file, we will see now that there are a lot more plots. So the first plot, which is the carrier waveform plot, is the same as before. I'm going to comment on this because I don't need it. Actually, I can just comment all of it out because I don't need to plot this anymore. We've already verified it. So I'll just click on toggle line comment, and I will come down and I will comment these two out because I don't need those. These are useful when you are generating publication quality plots, right? I don't need them now. So if you look, the first one contains the three currents, that is inductor current, input current, output current, that is the load current, and the second plot contains the voltages, which is the input voltage and the output voltage. Now, as already said, the circuit simulator takes care of the rest of the stuff. It extracts the time, which is the 0th column, and it extracts whatever variables that you choose as the appropriate columns. This is done internally. You do not have to do anything. You can, however, if you want, go and play around and beautify this to a greater extent if you want, right? You can put more labels, you can zoom, you can do any of those. That's always up to you. So I will save this file because I made these changes. Go over to the console and I will go to my other shell which has the buck converter, and this is where I'm going to run my autoplot.py file. So I will activate again my SP environment and I will clear the screen and I will run python autoplot.py. So we've now got these two plots, right? So the first plot, as you can see, is labeled as currents, contains the currents. The second plot is labeled as voltage and contains the voltages, which is the input voltage and the output voltage. So let's look at the currents. So I'm going to zoom in a little. So as you can see, the simulation is still running, right? We are still at 0.3 seconds. So the simulation is still running, and therefore you can plot your waveforms even while the simulation is running. You do not have to wait until the simulation ends. So I'm going to zoom in again so that I capture just a few waveforms. And now we are here. So this enables us, and here you see there is the key. So the blue line is the inductor current, the yellow or the orange line is the input current, and this green line, which is quite obvious, is the output current or the current drawn by the load. Now you can see here that at some point there is an overlap between the input current and the inductor current, and after that the inductor current diverges. So now we can very clearly, if you go back here, let's go to our operation principle, and you can see very clearly what's happening. When the power device is turned on, then the input supplies current to the inductor and the capacitor, and this is when the input current and the inductor current are the same. So therefore, in this first category, that is when the input current and the inductor current are the same, this is when the power device is turned on. So when the power device is turned on, the inductor current increases, and therefore the input current also increases because the input is supplying the inductor current. Right? Now during this period, the inductor current is exactly the same as the input current. This is when the power device turns off, and when the power device turns off, the input current falls to zero drastically, and that is obvious because when this power device is switched off, you'll see that there is no current in the current supplied by the input. This part of the circuit is cut off. Right? Now the inductor current freewheels through the diode, and as I already said, because it is freewheeling and it has no energy supply, that is why the current starts dropping. So this is when the power device turns off, and this is when the diode starts conducting. So the current is dropping, but as you can notice, the current does not reach zero. Before it reaches zero, the power device starts conducting again, and this is when the inductor current starts rising again, and the input starts supplying the input inductor current. And of course you can also see here there is the load current, or the current drawn by the load. Right? Now let us just minimize this and let us check out the other one. So here once again you can also zoom in here to the 24 volts, but it's pretty obvious because it's almost a constant voltage. Let's check out what output voltage we're getting. So you see we're getting a voltage around 8.4 volts. Now of course our objective was to get 9 volts, but as already said, an exact voltage will not be possible unless you do closed loop control. The reason is because there are drops, losses in each and every component. The switch has a loss, so this switch has a resistance. The input voltage has a resistance. The inductor has a resistance. Everything has a resistance, and therefore by the time this voltage, the voltage across the capacitor, will not be exactly as required, but rather there will be some losses due to all these resistances. If you want exact 9 volts, you must account for these, or you must do a closed loop control, one of them. So what really matters is if we zoom in further, you will see now there is a ripple, right? And if you compare this ripple with the inductor current, you will see that this rise in the capacitor voltage occurs when the power device is turned on, and the fall in the capacitor voltage occurs when the power device is turned off. Because when the power device is turned on, that is when the inductor and the capacitor receive energy from the input. And when the power device is turned off, the inductor freewheels through the diode. The inductor is supplying its own energy to the capacitor, but because the inductor current itself is falling, the capacitor voltage will also fall, right? So this is the operation of the DC to DC converter. So with this, I'm going to end this lecture. What we have achieved here in this lecture is we have completed the pulse width modulation for the DC to DC converter. We have verified the operation of the buck converter with respect to what we expected in theory. Now what is remaining is to perform a frequency response analysis on our output voltage and figure out what harmonics are present in the output voltage. And additionally, we can also find out what are the frequency if we measure this voltage, that is the switched voltage at the output of this switch or power device. What is the frequency response of this switch voltage versus what is the frequency response of this output voltage. So this will happen in the next lecture. So as before, if you did not get the same results that I got, or you found any other error, or you faced any other issues, please do post in the Q&A forum and I'll be happy to help you out. Otherwise, in the next lecture, we will look at how to do frequency response analysis on system or on simulation data, that is data which is obtained through the circuit simulator, right? So thank you so much for listening, and goodbye for now.